Hi, everyone. My name is Ajit Rajdev Singh, and I'm a Senior Solutions Architect with the Aerospace and Satellite Solutions Group at AWS. Today, I'm joined with my colleague, Ankita Gawali, who is a Solutions Architect for the Benelux region at AWS, and our very esteemed customer guest speaker, Grega Milczynski, who is the CEO and co-founder of Sinergise. Together, we'll be talking to you about building data lakes on AWS, and in specific, building your. Let's take a look at what we'll be covering in this session. We'll first take a look at the new realities or the requirements around how geospatial data has evolved over the years and what requirements around geospatial analytics are customers seeing. Secondly, we'll take a look at the AWS services that you can use to build your data lake powered or for your geospatial data. Then we'll take a look at or dive deep into some services which can help you to build a data lake architecture or data platform architecture which can grow as per your needs and which can scale down when you don't need it to. And then finally, we'll bring it all together with a short demo which will be presented by my colleague Ankita. Finally, we'll have the guest speaker session from Grega, who will speak about Sinergise and the rich set of web services they have developed around Earth observation analytics, which makes it easy for customers to develop their geospatial analytics capabilities. So let's dive right in. So the requirements around geospatial data and analytics can be characterized into three main trends. Let's start with the business first. We are seeing businesses are transforming and evolving at a faster clip than ever before. At the core of this transformation is data. Business leaders are leveraging data to take key decisions about which direction their businesses need to go. And customers have realized the value of geospatial analytics in this data strategy. For example, insurance companies are now using geospatial data to understand the insurance claim, to validate the insurance claims. Logistics companies are leveraging geospatial data to optimize their supply chain operations. Even retail companies are leveraging geospatial data to understand where their product, which geography their product fits in best. So it's quite clear that business leaders want their data team to build a data platform, data processing architecture, which can support these kind of analytics. Secondly, there is a large swathe of data that is available in this space. We have low Earth observation satellites, which are cheaper than ever to send into orbit, and they send us imagery back. There are drones. There are geotagged social media posts. There are devices, like mobile devices, that send geotagged posts. And then there are spatially intelligent IoT sensors that send semi-structured, structured, or unstructured data into your data platform for analysis, right? And then finally, with these amount of sources, with so many sources, you have number of data formats. As I already described, the satellites will have its own data standard. Data coming in from your sensors will be its own data standard, right? So customers are really looking to be able to leverage all these different sources and also manage the different standards that come with these sources. So in a nutshell, what exactly do customers want to realize their data strategy powered for geospatial data is a single data store that can provide them with a virtually unlimited scaling and in storage at a cost-effective approach, at a cost-effective factor, right? Secondly, they want to be able to use the data standards of their choice. They want to be able to use the sources of their choice. They don't want to be limited by the definition or by the technology that they are using in their data platform and discount some sources from their strategy. And finally, they want to be able to analyze the data the way they want, going from all the way to traditional analytics using business reporting tools, all the way to advanced machine learning analysis. So they can combine multiple data sets together. They can use their historical data to understand what's the trend going and what should they be doing with that data. So cloud data lakes actually help customers meet all of these requirements. Starting from the very bottom, if you look at the networking ecosystem that cloud services provide, customers can leverage these networking services to get data from their on-premises or from their existing data stores into the cloud data lake, as well as they can use the streaming services to get data from streaming platforms like IoT sensors or social media posts into the platform. Secondly, services like Amazon S3, which really form the foundation of your cloud data lake, allow you to decouple the storage and compute, which is impossible doing it on premises, right? So if you want to increase your storage, traditionally you had to increase the compute as well. But now, with this decoupling, you can really increase your storage without actually the compute and keep the costs low. You have services like AWS Glue, which allow you to manage your ETL functions without actually having to worry about managing the infrastructure that comes with it. You can write your Python Spark or Scala code or Spark code and just run that code without actually needing to worry about how my infrastructure will scale depend on or based on my ETL jobs. And underpinning all of this is security and governance provided by the cloud platform, right? Customers are able to use the rich set of security and governance tools that these cloud platform provides to be able to meet the requirements of their customers about data security and also the regulatory compliance that they may have. And finally, with ever-increasing list of analysis services, like you already have the big data processing analytics, you have the data warehouse processing capabilities provided by cloud, and then all the way to real-time analytics and machine learning analytics. So it really fits into very well with all the requirements that we just saw around geospatial analytics. So now that we know that cloud is the way to go forward to build your geospatial data lake, let's take a look at why AWS is the choice of platform for customers to do so. So this is a typical data platform architecture. You may be familiar with the blocks that I'm showing here. The 7 blocks kind of show a typical data platform from left all the way to right. If you look at all the way to left, you have the sources that leverage the services in ingestion layer to ingest different types of data, which can then get processed either in a batch format or in a real-time format, and then it is stored in a serving layer. The serving layer really comprises of data stores which are optimized for analysis, right? So you may have a front end or a web application that's need to be backed by a database which supports GIS or geospatial data extensions. That is in the serving layer. And finally, the process and analysis layer consists of your reporting tools, consists of your machine learning inferences that allow you to get your inferences out. So what I'm going to be doing is, in each of these blocks, I'm going to be mapping the AWS services, and we'll be using the depth and breadth of AWS services to really fulfill these blocks in a way that meets the requirements that you have. You may want to do machine learning, you can choose a service that does machine learning. You may want to do just business reporting, just kind of trying to understand which geography my product is being used at, and you can use a data warehouse for that. So let's go ahead and do that. Starting with the sources, as we already discussed, the spectrum for geospatial data sources is quite wide. You have satellite imagery that can put in raw satellite images, and you may have public or commercial data sets, which may be, say, for example, coming from your Sentinel-1 and Sentinel-2 satellites, from Landsat satellite, or you may have contracts with your commercial data providers, which can be a source of data. You may already have historical anecdotal data on your on-premises that you want to bring into your data platform. And finally, IoT sensors, social media, and mobile devices are adding more unstructured data into your data lake. Services like AWS Ground Station gives you a global network of fully managed ground station, which allows you to downlink the data from your own satellites directly into your data lake running in AWS. Secondly, services like data exchange and open data, which I will actually go into or zoom in on a bit in further slides, allow you to actually subscribe to your data providers or search through a catalog of open or public data sets. And then networking services like Direct Connect allow you to connect to your on-premises and get that data in your data platform. Similarly, IoT Core and Amazon Kinesis can allow you to get your data from streaming IoT devices into your platform. And this data, we saw, is of different form, raw satellite imagery. It can be a structured geospatial data of, say, in a NetCDF or HDF format, or more newer forms like cloud-optimized TIFFs or GeoTIFFs. You can already have GeoJSON files or unstructured data coming just as JSON files with varied fields. You want to be able to store all of this data without actually compromising on getting or losing any of this data. And the foundation of this data lake is the Amazon S3 bucket. Amazon S3 bucket is an object store. It doesn't put any restrictions on what kind of data you can put in there. You can put an image, you can put a JSON file, you can put an Excel file, if you will. Any kind of file, it can go in S3 bucket. So that really forms the foundation of your data lake, from where you can then start transforming it in a way you want, right? So you would want to enhance it, say further crop your image to the area of interest for some particular location, or you would want to only extract certain bands. Say, for example, you want to identify the vegetation index in a particular area. So you only work with, say, band 3 or band 4 of that image, right? And that processing that you want to do also has various, there are various services that allow you to do that processing. You can do your own processing, bring your own logic with Amazon EC2, or you can do it using Amazon EMR, which allows you to run managed Hadoop cluster, or you can do a machine learning-based transformation with Amazon SageMaker. When you are done with this transformation, you can use AWS Glue to transform that into a data store that is optimized for your further analysis, and that is in the serving layer. So we have optimized data stores like Amazon RDS, which supports Postgres extensions, or Amazon Redshift, which is a data warehouse and which also supports GIS extensions. And finally, the process and analyze layer also has many services that you can choose from, all the way from QuickSight, which just allows you to visualize directly from your data, to Amazon SageMaker, which allows you to do machine learning inferences from your trained machine learning models. So zooming in, I want to focus on a few key services that allow you to get started right away. And we will also be looking at these services in the demo that Ankita will present in a while. The very first service is Registry of Open Data. This is powered by Amazon S3, and it has over 300 data sets, public data sets that you can subscribe to, that you can get directly into your AWS account. And the storage, there is no storage cost here. AWS takes care of the storage cost. So you have access to this petabytes of data, and you can really search through this catalog and get started right away. And later on, we'll see in the Sinergise session how Sinergise makes it possible to easily search through this data, how their web services make it easy for customers to consume this data in their platform. The next service I want to talk to you about is data exchange. The Open Data Registry is for public data sets. Data exchange is a service, you can think of it as a marketplace. Whether you are a subscriber, if you want a commercial data provider and you want to subscribe to a commercial data set, you can go and search that data set on data exchange and get it easily in your environment. Or if you are a data provider, you can actually outreach and increase your revenue channels by putting your data on data exchange, and then you have access to this reach to millions of AWS customers. In a nutshell, if you are leveraging the data platforms on cloud, you are able to reach to a global community of users. You are able to use the new services and tools provided by AWS, and you are able to lower the cost of your research. The next service that I want to talk to you about is AWS Lambda. AWS Lambda allows you to run your code without managing any infrastructure, right? No servers that need to be managed. So say, for example, you have some ad hoc, we want to do some ad hoc operation on your data. Like an image is coming in, and you want to crop it to area of interest. You don't want to manage your instances. You can run an AWS Lambda code and let that do it. AWS Lambda layers allow you to bring your own runtime, so you're not restricted with the runtime that is provided by AWS, but you can bring your own code and share those dependencies across multiple Lambda functions. And finally, AWS Glue. AWS Glue is a fully managed ETL service, and it provides you services in all 3 ETL functions that you can think of. Fully managed data cataloging with Hive meta store, so you can catalog your data and store in a scalable Hive meta store. Job authoring, it provides you pre-fulfilled or auto-generated ETL code that you can use as a boilerplate or starting point and then iterate on top of it. And finally, job execution. It can allow you to run the jobs on a periodic or on an event basis without actually managing any infrastructure. So with that, I'd like to give it over to Ankita so that she can walk you through a demo with all these services.
Climate change continues to have a profound effect on the quality of life that we live. And as a result, research into sustainability is growing. Researchers are planning for the future by looking at climate recorded history, as well as creating climate forecasting models. In order to drive this research, it's important to have access to high-quality data set. Through AWS's collaboration with NOAA Big Data Project, we have access to over 200 years worth of climate data. And today, we are going to see, with just a few steps on Amazon Web Services, how we can improve accessibility to this data and do data exploration and analysis. So as you can see, the NOAA bucket, it consists of data right from 1763 to present. And this data set is made available and maintained by the NOAA and US Department of Commerce. In order to access this data, we can do so using Amazon Simple Storage Service. All of this data is available publicly on this data set. So let's go and have a closer look at what this data set consists of. As you can see, this is the NOAA bucket, and it consists of data files arranged in the form of CSV, and each arranged in the form of year. The most common parameters inside this data includes daily temperature, precipitation index, snowfall, which are really important parameters for assessing risks of extreme weather conditions. And we're going to use this data for further exploration and analysis in today's first part of the demo. So the demo walkthrough is as follows. As you can see on the screen, we are going to start with the middle portion, that is Amazon Athena. Amazon Athena is an interactive query service which uses SQL and Presto in order to query a number of different sources like JSON, CSV, and Parquet format data. Amazon Athena, out of the box, integrates with AWS Glue, which is an extract, transform, and load service that directly talks to the NOAA S3 bucket. And the most important part that AWS Glue serves here is that it makes the data in NOAA bucket available in the form of tables. It also maintains a metadata catalog so that we can query the data very easily. Further, as we are going to query this data, we are also going to stage the results of the query. And we're going to see the performance implication of doing this operation as well in the demo. And once we have this data in our staging environment that is inside our private S3 bucket, we are going to further visualize this data on Amazon QuickSight. Amazon QuickSight is a business intelligence dashboarding service, which we're going to look further into. So here you can see a very simple query that is I'm doing in Amazon Athena, that is select star. And I'm taking a table as reference. And this table I'm getting from AWS Glue. As you can see on the console, AWS Glue, I've created a table that directly talks to the Noah S3 bucket. Okay? This ensures that the entire data in Noah bucket is available in the form of tables. We also have the schema information in the form of metadata. And you can notice the quality flags associated with this data set, which ensures high quality of data. And I'm going to use the Glue table as reference for querying the data set. So doing select star from, as you can see, this is an external S3 bucket, right, on the registry of open data. I've gone ahead and queried the data, and you see that it took about 6 minutes to query over 97 GBs of data. How about we improvise the performance of this operation even more so that it yields more and more productivity, right, as you are doing data exploration? So I'm going to create a staging environment inside my own account, inside my own S3 bucket, where I'm going to save the result of the query and further compress that into a Parquet format, which is a columnar format for data storage. It makes it super easy to store as well as query the data. And now I'm going to use a table from Athena to access this staging environment. Using this staging environment and this staging table, it's going to give us enormous performance improvement in doing simple queries on top of this geospatial data. So let's go ahead and look at what this query looks, what is the performance implication of doing a similar query, but this time on the staging environment. And you can see that I'm selecting and counting the number of observations, and this time it took just 1.4 seconds to go through the entire data set. Remember, we're talking about over 200 years worth of data over here, which is over millions of observations collected by weather stations around the globe. So naturally, if you want to have confidence into the results for your climate change research, you also want to trace the lineage from where the data is coming. So essentially, which weather stations are recording this information. So I've also created a similar data repository for the number of stations. And as you can see, this is over 119,000 weather stations that are collecting climate data worldwide. So I'm going to use this data, the observation, as well as the weather station information in order to understand even more in detail about my data set. This time, I want to query 200 years of data, but I also want to see the climate change, the drastic differences in the results, and which is why I'm choosing 30 years of interval of time, as you can see, from 1836 to 2016. This would give me, at least my expectation is that it would give me some drastic changes in the numbers. And now you can see we have an even more detailed data set with supporting weather stations as well as the data values associated with it so that we can have confidence in our research and in the result. I'm going to go ahead and further visualize this in Amazon QuickSight, which is the business intelligence dashboarding service I'm using. And you can see that this is a growth analysis heat map that shows an overall trend of the number of weather stations improving, right? From 1926 to 2016, we have an overall growth trend in the number of weather stations that are increasing, and they are the ones who are actually collecting this valuable weather and climate change information. Further on, I'm also going to look at where are these weather stations located. For example, I'm creating a geospatial map over here in order to understand what is the location of this data. As you can see, there are more and more blue dots on the screen which are corresponding to the recent years, that is around 2016 and 1986, compared to the older times when there were very few weather stations gathering climate change information. And you can see that with a very simple drag and drop interface, you can make a number of visuals and a number of custom dashboards in order to study and understand your data set. For example, over here, you can also see the density of the weather stations, for example, who are collecting this information. And then you can further build up on this, right? You can go to and find out a particular region and then associate your weather data with that region and explore the data itself. So I hope that this example has given you an end-to-end understanding of how first you can improve your accessibility to the data by creating a staging environment and further make queries on top of this data and visualize it. Moving on, satellite imagery. Satellite imagery plays a crucial role in climate change research, right? Today we are going to do a satellite image exploration of a certain region, that is, I'm choosing the Reunion Islands, where there was a recent volcanic eruption that happened in the last quarter of 2021. And I'm going to visualize that data. But let's talk about where are we going to get the data from. So Sentinel-2 maintains a global data of satellites from November 2016 around Europe and globally since 2017. And this data is also made available on the Registry of Open Data through Simple Storage Service. And this entire data set is maintained by Sinergise. Sinergise not only makes this valuable data set available to us, but they also make a number of different APIs and tools in the form of Sentinel Hub available for deriving analysis for satellite imagery. Remember, the scale that we are talking about here is over petabytes of data. Unlike the first example, we really need to be prudent in order to query and understand and make analysis on satellite imagery. So let's see a step-by-step demonstration of how we are going to get to the data exploration step. For this, starting with the Reunion Islands, right? They are located at this latitude and longitude location, and I'm going to use Sentinel Hub request builder tool in order to get the latitude and longitude location of the Reunion Islands. That is, I'm essentially finding my area of interest, okay? Now that we have this data, let's look at the volcanic eruption which we are going to study, and it is happening mostly in the southern part of the island, and around the time range of last quarter of 2021, right? We're going to use Amazon SageMaker, which is a fully managed machine learning service. It integrates very well with Jupyter Lab and Jupyter Notebook that makes it super easy to do data exploration and analysis. Similarly, I have created a Jupyter Notebook in Amazon SageMaker in order to do data exploration. This time, I'm using Sentinel Hub APIs in order to derive the satellite imagery. As you can see, I'm going to create, I've fed the location coordinates in my code. I'm also using the WMS request from the API in order to feed the time range, the location coordinates, as well as the length and width of the image that I'm expecting. And as you can see on the screen, just moments before the volcanic eruption happened, this is how the Reunion Islands looked like. And this is a pretty high quality image for a 4,000 kilometer square space of area, by the way. So moments after the volcanic eruption, there was sulfur fumes in the air, and you can see the impact that it has left on this particular island. You can also see the lava, actual lava in some of the pictures here. Maybe zooming in, you can see it even more. So this is really critical pieces of information that we have access to with just few steps using Amazon SageMaker to query external APIs like Sentinel Hub in order to have access to satellite imagery. This gives us a deeper understanding of the impact on certain geographical locations and study climate change research. Similarly, we can also use satellite imagery in order to just look at the different formations around the world, right? Like vegetation index, glaciers, or ice formation. Today, I've taken an example of ice formation over the Caspian Sea. The Caspian Sea froze over the winter of 2020, which caused a very thick layer of ice to be formed. around in December 2020. And you can see in the picture around 2020, we had this really thick layer of ice, which eventually started melting towards the Jan of 2021. And you can see the drastic changes in this image, right? And which represents the melting of ice, and we've taken this image from the satellite data. It's essential to understand that when we are talking about petabytes of data, that is satellite imagery, Sentinel Hub APIs plays a very important role in order to give us access to this help us find the right satellite imagery, and also drill down and get access to this highly valuable data set. And you can see that it takes very few minutes to set this up and study for climate change. So in order to summarize, we saw two different examples where we've done data exploration and data visualization at two completely different scales of data. And I hope that this demo has been useful, and I hope that you're inspired from it as well. So I'm going to pass the stage on to Gregor, who's going to talk to us more about satellite imagery. Thank you.
Thank you, Ankita, for this nice presentation. So yeah, we have all this data available on S3, easily accessible, and it's extremely valuable, right? Literally valuable, because European Union and United States, they have invested billions of euros to actually create this data. And because of the free and open policy, it's now available for anyone to use. But it's not easy to do so. I mean, if not for us, because of the sheer volume of more than 50 petabytes of data that is out there. And this is what we recognize as a business opportunity at Sinergise, and we created Sentinel Hub, which is kind of AWS of the Earth observation, a set of APIs on top of AWS, which kind of make this data available in a seamless and easy and fast manner. One harmonized API which provides access to all these different data collections, and done in a way that it can be easily integrated in machine learning workflows, in web application, desktop application, mobile, whatever you want, or Jupyter notebooks like what Ankita showed. And if you're not familiar with it, I would recommend that you head off to the EO browser and you go to the favorite place in the world and you search for the latest imagery that is available there. Probably it will be from the last couple of days or maybe even a couple of hours. And then you can look at it, you can zoom in to all the relevant details. You can go back in time for 1 or 2 months, or maybe you can go back in time for a couple of decades. And then you can make some processing on top of it so that you extract the information, in this case, which parts were deforested because of the agriculture. And then once you're happy with the script, you can then process this through time so that you can see how the planet is changing. It's really, really valuable resource, and it's extremely important for the climate change now, because it really provides us insight into what's happening. Now, Sentinel Hub is not about visualization, right? Sentinel Hub is a set of APIs which provides analysis-ready data. And this depends on what kind of analysis you are working on. You might want to get original reflectance data directly from the satellite, or you might want to get a vegetation index or an image, or maybe you would prefer to have a statistics over a longer period of time. Whatever the one would like to do, it's available via one API. And it's a typical RESTful API, easy to use. We have also the OGC compliant API for those which are using the tools that have this supported. And this example shows how easy it is to actually access the data, right? I mean, if you do it by yourself, you would need to make a script that would go to the S3, download the relevant data, decode it, stitch the neighboring scenes, do some mosaicing and some further steps on it, reproject in your coordinate system. Or you can simply say what you would like to get, for which time period, in which area, and then maybe if you want some additional parameters, and you get it immediately. It's extremely fast, so it takes about half a second to process all these requests. And maybe here, worth mentioning that we do all these things on the fly. So in half a second, we would go to S3, So we would first parse your request, check what you actually want. We would go to S3, find between 50 petabytes the relevant pixels that you would like to process. We would get them, do all this decoding and so on, and then fetch the data to you. And that's kind of magic that you can do this that fast. And it's fast enough that you can directly integrate it in the application, like what you've seen with the EO browser, right? It can be done on the fly. Now, for those working in machine learning, especially if you are working on the object level, like, I don't know, checking the agriculture parcel, maybe rather than pixels, you would work with the statistics, because you can aggregate all these pixels into one JSON file, and you would have more or less all the information of the signal, but yet orders of magnitude less, and it makes it so much easier to process further on. Now, you can do some level of processing on top of the data, like you can create all the well-known composites or the vegetation indices or other indices. You can even do some neural network, put it in there and run the inference directly on the data. And these scripts themselves are actually valuable because it's a knowledge that was built over decades in the remote sensing community, and we decided to basically put everything on GitHub under MIT license so that anyone can come and take the relevant processing script and then just tweak it to whatever they would like and make use of it. As an example, that's a burn ratio before the fire and then burn ratio after the fire, and you can make a simple script comparing these two data sets from different dates, and you get results in an interactive fashion showing you which parts of the area were severely damaged, which only moderately, and which were not touched by the fire at all. Another example, this one is combining data coming from different sensors. So we use radar Sentinel-1 data to recognize whether a part of it of the area is build-up area or it's not. If it's build-up area, it's marked with pink or green. If it's not, then we would show the data coming from Sentinel-2 displaying the vegetation. So you can do both of the sensors at the same time. Similar example, we have Sentinel-2, and then we create the normalized vegetation index, which is like the most well-known index to check the level of the vegetation, but the optical data don't penetrate the clouds, so you have the gap there. And what you can do, you can take the radar-derived data and basically mix it together so that you have best of both worlds. For those working with radar data, this is one level more complicated than the optical, because the data needs to be first auto-rectified and radiometrically terrain corrected and all the steps that you need to do. Again, complicated, but with the API, just another parameter to do, and you get the data in an analysis-ready form as well. Now, Sentinel Hub provides access to basically all the relevant open collections: Sentinel, Landsat, MODIS, Digital Elevation Model, Copernicus services. You can even get access to some commercial data, VHR, like PlanetScope, Pleiades, Spot, and so on. Altogether, more than 50 petabytes of data available with one API request. Now, importantly, these collections are all also updated, so you don't need to worry whether the new data will come there or not. Obviously, we don't support all the data because there's so much of variety, which is why we build the Bring Your Own Data, like a self-serving facility where you can take your own data and put it on the S3 storage in one of the standards format, like Cloud Optimized GeoTIFF or ZAR, and then you register it in Sentinel Hub, and suddenly you can do all the functions of Sentinel Hub on top of your data. So we build this having in mind that people will bring the commercial imagery that they bought or the drone imagery, but then we recognize that it's even more useful for the machine learning, for the derived data. So typically, you get the label data, which you would often also ingest in the Sentinel Hub so that you can use it for the labels in the process. And then you have results, again, coming directly from the procedure into the S3, can be registered to Sentinel Hub all at the same moment. And then you can use the scripts to kind of compare these two interactively so that you get immediate feedback on how good your machine learning workflow is working. Machine learning is obviously very relevant when you have so much of data that you literally cannot visualize and check everything by yourself. So this is why we need to use machine learning procedures to basically extract the relevant information. And we built some tools specialized for that. One of them is batch processing, which basically creates features for the machine learning. When you do machine learning on the satellite data, you typically take a time stack of 1 year of data. You would want to remove the clouds because clouds are typically not working very well in machine learning procedures. And then you would fill the gaps that you created by removing the clouds with interpolated data, do some harmonization, and then have this feature delivered to TensorFlow as an example. And so what we did is that you can configure this process of what you'd like to do with the data and say, now I'd like to have it running over the large area. And we will split this area into small chunks that are just the perfect size to be used in the machine learning. And then we would process it, and then we would output this to the S3 storage so that you can then immediately use it in the machine learning. Again, similarly, if you're working on the object level and you would rather work with statistics than with actual pixels, you can create the processing script. You can put the geo package with hundreds of thousands of polygons and say, look, have it running, and we will deliver the JSON files to the S3, where, again, you can use them in the procedure further on. Now, Sentinel Hub is used quite a bit. We process about 500 million requests every month. We stream the data to about 400,000 IPs worldwide every month. And yeah, every month we add another petabyte or so of data to the collection. Now, with the data being available in such an easy and seamless manner, then you have users with different backgrounds, different interests, different know-how that actually make use of this. And they create things that we would never imagine that one can do with the data. The examples I like most is, for example, these scientists which were looking for penguin poo in order to identify the penguin colonies in Antarctica. I mean, penguin is so small that you cannot see it on the satellite image, but if you search for the shit of the penguin, you will actually see it where they are, and you'll know that they are there. Another example, this guy used your browser to geolocate this photo that was taken by a lost hiker, sent to the friend by a mobile phone, but without the geolocation. And he used EO browser, where he was able to get like most recent satellite data from a couple of days ago, and was able to kind of see where exactly this guy is sitting, accurately enough that he was able to send the search and rescue team to that location, and basically they found him, and possibly he saved his life. That being said, most of the use is actually commercial. People building applications, that's a typical precision farming application, class crop view, where they take the data and they convert it into a signal telling you how the specific field is working, how good it is evolving. And you can then use this to see which parts of the field are working better and which not. And then you can basically extract this data and put it into the tractor to use the relevant amount of fertilizer in some parts. Another nice example, Tomtom, they used our services to basically build global land cover map of like on the whole world, so that they can use it in their maps. They did this over a couple of months, really something that one would not imagine that is possible. But it's not just what you use the data for, it's also important how you use it. That's an example by Joint Research Center and Google, where they build the global surface water explorer, which is a super cool tool that provides you information of whether there was water there over some period of time. They processed all the Landsat data and as well as the Sentinel recently, and basically you can click to any place in the world and see whether there was data in specific time periods. And again, it's a very important one because it gives you information of how the drought is affecting different parts of the world. But, I mean, what they said is that they used more than 10 million compute hours to process this data. And that's a lot. I mean, that's really a lot. And it basically contributes to the climate change by itself. So we were thinking of, can we do this a bit differently? And we tried to address the same problem, but from a bit different angle. So we said we'll only focus to the water reservoirs, because this is what they are really important for, obviously, the water uptake. And we identified about 15,000 of them worldwide. We didn't focus to the ocean. We know that the water is there. We didn't focus to Sahara because there is no water there. We really focused to the water reservoirs that are there. And then we made a script that basically every time that checks whether there is a new data available, every time that is taken, extracts the water extent, and then put it in a database so that you can have this kind of analysis. The result is very much similar, but the way how this is done is way more optimized. I mean, this can run in Lambda, right? And it costs less than 100 euros a month to operate, so it's way less than the compute times that I mentioned previously. Another example that we did is we basically wanted to create machine learning features for testing various classification algorithms on a global scale. So we processed 18 months of Sentinel-2 data, which would be about 3 petabytes of data, and condensed them into 120-meter resolution features, 10 daily features, which are really, I mean, easy way to start with for the machine learning. So to process this, again, we used the 120-meter because we didn't want to consume too much of resources, and we were able to process this for about 500 euros, right? Even though it's 3 petabytes of data that we processed. While doing that, we were hitting S3 quite a bit. So you can see on this chart for a couple of hours, basically we hit it with hundreds of thousands of requests per second. And it worked quite nicely, which is impressive by itself. Now, obviously, when we created this result, we also wanted to make it available to others so that they wouldn't need to run the same processing, and we put it on the Open Data Registry on AWS because it was an obvious thing to do. So thank you very much. Some links to find more information, and looking forward to see you use that. Thank you.